Representing enthalpy. There are four methods to represent enthalpy. The first method is through a thermochemical equation. We just find the delta H and fit it into that equation. First, like always, create a balanced chemical equation. I balanced it for you. So what is the compound in question that is being burned? It's 2 moles of butane. So in our question, in order to find the delta H, the moles here is going to be the 2 moles of that compound being burned in question. And then for every mole of that, so the molar enthalpy, so for every mole of that is being burned, it is releasing this much energy. And then diagonally they cancel out, so this cancels out, this cancels out. Find the product, I get negative 5,742 kilojoules. Where am I going to be putting that? Reactant side or the product side? I have to put it on the product side. Because it's exothermic, it has to be on the product side. And I don't need to put it into a negative. It's already a negative, even though it says a positive here, because it's on the product side. If this value was over here, then it would stay as positive. Next, method number 2 is finding the delta H value. So similarly, like the previous example, this compound here is being burned, it's combusting, and it's making sulfur trioxide. So for every 2 moles of SO2, because that's sulfur dioxide in question that is being burned, 2 moles of that is going to be put into the formula. And then for every mole of that, how much is it burning? It's burning this much energy. I'm just going to cancel out these units. I end up getting negative 197.8 kilojoules. Okay, now all I need to put is at the very end, delta H, so on the right side, delta H is equal to its respective symbol, so it's negative, so I just have to put it that way. I just put kilojoules. If it was positive, then I would just put positive here. Method number 3 is the standard molar enthalpy. So it takes into account final and initial conditions. So initially, if it starts at SATP and it reacts and then eventually it's going to cool and go back down at the end, back to SATP, there are predetermined sets of values. So for methanol here, it's negative 128.6 kilojoules per mole. But the question is asking for the standard molar enthalpy of hydrogen. Well, for every mole of hydrogen that is being burned to create that, we have 2 moles as a coefficient here, so I just have to divide by 2, so I just get 1 mole of the hydrogen, but it has to be proportionate to the methanol, so I have to divide it by 2 over here, so I end up getting negative 64.3 kilojoules. So for delta HR, the not here symbol is determined here as the standard molar enthalpy, that preset value. So it's just going to be negative 64.3 kilojoules, and you also have to put per mole and the compound or the element, so H2 in question. It's important to remember that. Method number 4 is a potential energy diagram. So I just find the reactants, then find the products, find the difference between that. So that's going to be the delta H. Delta H is also known as this change in potential energy.